Good morning, everyone. This session is on LFA, loop-free alternate. I am Luc Degene. I'm a technical leader, services. I'm part of the tech team for a long time doing routing, multicast, and PLS out of the Brussels tech office. So we have a 2-hour session. Thanks for showing up. I know it's the last session of the day, of the week. I also know if you have to leave early, catch a flight, whatever, that's fine. Just go, no problem. This is the agenda of today. So we'll have an introduction, a rather large part on the architecture or the theory. Then more practical stuff, configuration, implementation, even troubleshooting. And then a couple of other topics, LFA, WAE, and so on. If you have any questions, just ask. I'll try to answer them. If there are too many questions, we can take them offline. We have a Spark board, so you can, for the next 2 weeks, I believe, still ask a question there. I will answer them. The PDF, I posted it this morning. It was not online yet on the app, but it seems to be there already since a few minutes, so that's fine. However, I do encourage you to follow the slides here and not on the PDF. It makes it a little bit more interactive. Let's get started. So what do you need to know? Not much. You need to have a little bit of basic knowledge on routing, forwarding. So the routing table, the RIP, we call it, and the forwarding table or the hardware, so in the data plane. We call that the CEF table, that's Cisco speak. IETF speak would be the FIP table. That's basically all you need to know. Some basic understanding on OSPF, ISIS, maybe EIGRP, that will help as well, but not much more. I do not cover platform support anywhere, so you don't need platform knowledge, right? Why is that? One, I wanted to keep it easy for me, otherwise it becomes bloated because we have so many platforms, right? We have iOS, iOS XR, Nexus. So too many platforms to cover, too many software releases to cover. If you have questions on support, I would take it offline. So after the session, we can ask a question. I'll be here for a while, or on the Spark board. Right? Any other question, you can ask live. No problem. So let's get started. What about failures? Well, in the past, let's say 20 years, when I started working at Cisco, we didn't care too much how fast things were converging in your network, right? We just said, it runs on TCP, so let the higher layers take care of it. So we had rerouting in seconds, and that was fine. Nobody's life depended on it. You see that nice box there, AGS Plus from a long time ago. Then later we said, no, we want faster convergence because we have time-sensitive applications there. So we're going to do something which is easy, just make the routing protocols go faster, right? So we tune OSPF, ISIS, maybe EIGRP, so that they just are faster. And we got the convergence time down until 1 second. You can't do that forever. There's a limit to speeding up things. Then we said, well, today with all the voice and video applications, we really need it to be extremely fast. Let's say 50 milliseconds. Where does the 50 milliseconds come from? Originally from the SONET APS protection we had in networks, and later it was taken over by traffic engineering and PLS. So the goal is 50 milliseconds. That's kind of good enough. If you're on a phone call, you reroute under 50 milliseconds, you won't notice it. Okay? But for that, we need to have pre-computed backup repair paths. So backup paths ready to be used. That's what this presentation is about. Sorry. So what are the goals? First of all, we're going to take what we already know and works well. So from traffic engineering, we looked at fast restoration, link protection, even node protection, and so on. These are the good things. We try to keep them. What are the bad things? Well, traffic engineering was bloated. It has a lot of signaling, soft state signaling, RCP. It's periodic signaling. We had a lot of bandwidth calculation going on and so on. And we even had path protection. Now, path protection is end-to-end protection. It's very nice to have, but you can't do it in 50 milliseconds. It's a few hundreds of milliseconds. So we're going to leave it out. On top of that, we want everything to be simpler with LFA. That's a goal. Incremental deployment, and that's very important. Everything we do with LFA, there are always exceptions, there are a few exceptions, but let's just say, for 2/3 of this presentation, everything we do with LFA is on one router. Nothing gets out, no signaling protocol, there's no RFCs with packet formats, anything like that. So you can deploy it on one router, then on the next, and so on. MPLS is not needed. You don't, just IPv4 or IPv6 is fine. However, if MPLS is there, that's fine, it will work too. One note, I only talk about IPv4, not IPv6, but usually what we have for IPv4 is there for IPv6 as well. The only problem with IPv6 is that the addresses are longer, so you can fit less of them on the slides. Those are the goals. A couple of important notes. Coverage. Coverage is a big thing with LFA because it's not guaranteed. So if you deploy LFA and you want to protect all your prefixes, maybe that will happen, maybe not. We do not guarantee it, right? We never guarantee anything. If you want to guarantee, you have to go to a shop, buy a coffee machine, you get a paper signed, 2 years guarantee. That's not what you get. But the coverage will be topology dependent. So really meshed topology, very good coverage. Not meshed, not so good. However, we are Cisco, we always come up with a solution. Even if your coverage is not good enough, it's not 100%, at the end, we will say what you could do to have 100% coverage. And also important is only one repair path, always. We never go for 2 backups, 3 backups, and so on, right? It doesn't make sense. It's too much overhead, one repair path. Any questions so far? Alrighty. The architecture of loop-free alternate IP-fast reroute. This is the boring part. You have to set through it. There's no other way. So what do we have? We will always talk here about a primary path. Sometimes the link is in red. This is the link we are protecting, protected link, hopefully. We are going to protect it with a repair path. So for prefixes, we are going to try to find an alternate next hop, in this case, router C, for any prefix over the red link. All right? That's the repair path. We will pre-compute it, and for the IGP, by the way, whatever we do here in this presentation is IGP. There's no BGP. BGP, different topic. BGP PIC, prefix independent convergence, and so on. That's something else. So what do you need to do? You need to enable LFA. You will see, at the minimum, you need to configure one line, one command. During the repair, of course, the link is gone. So A will have to reroute, switch the traffic towards C. The only thing we need to make sure is that router A detects the link going down very quickly. You really must have BFD. You must detect the link going down in a few hundred milliseconds, maximum. Should be less. If you don't do this, depending on the platform and so on, it can take up to a second. So that's useless. If you forget this, everything you do after this, configure LFA and so on, do the testing, it's useless. Everything gets rerouted in more than 1 second. So that's pointless. So you must have BFD, lightweight protocol, can run on line cards and so on very fast. So it just detects that the link is going down and tells the client, in this case the routing protocol, OSPF, ISIS, the link has gone down, so do something. Switch your routes. After, we always still have another event, a regular convergence. In a link state protocol, this will be SPF, Dijkstra algorithm running. And then it's possible that we move the paths again to another, the prefixes to another path. This is what we call the PC path, the post-convergence path. This is after a regular SPF run, maybe even a few seconds after the link going down. It also means that the traffic is on the backup path for a relatively short period of time, maybe just a second or less. There's nothing to do here. Repair calculation. Now, keep in mind, router A is the calculating router. You have a protected path here, protected link, and all the prefixes have the primary path over that link. Router A needs to calculate a path, a route through the network, which is a backup route. But the only thing we really care, or the only thing router A really cares about, is finding an alternate next hop, router C. That's it. Router A does not verify the path with a signaling protocol like in RSVP, TE, traffic engineering, or anything like that, right? We just need to find an alternate next hop. So everything is local to router A. So the repair path, all right, so it will be the alternate next hop, in this case, router C. The post-convergence path, we don't know. There are no metrics here, but it could be this path over C, or it could be this path. We don't care. After the link has gone down, we switch the traffic to backup path. It's fine, we didn't drop many packets, up to 50 milliseconds. A few seconds later, SPF runs if it's a link state protocol, and then the traffic might switch over again to another path, but without dropping traffic. Reducing loss of connectivity. All right. So how does it work when we have more than one prefix? First of all, we need a failure detection. It needs to be quick, so you really should have BFD. Failure propagation, so whatever protocol you have, there's flooding, there are updates being sent out, so that the other routers know about the event. We calculate a new topology, new paths, and we put those prefixes, paths, into the routing table. And then we put the prefixes one by one into the routing table and into the forwarding table, the FIP table or CEF table. Right? So this takes quite a bit of time without protection. With protection, so LFA on, let's say 50 milliseconds later, we hit the repair time. All the prefixes will be switched over to the backup path at the same time. Everything that happened here after that, we don't care anymore. There will still be flooding in OSPF ISIS. There will be routing table, FIP table update. We don't care, whatever. That's all fine. We just need to make sure that everything happened here in under 50 milliseconds. And the important part is that all the prefixes will be updated at the same time. What is the main idea behind LFA? You have a primary path for multiple prefixes, no doubt. That primary path has a primary next hop. So that link between you and the next hop, the primary next hop, we want to protect it. So we need to find an alternate next hop. And we must make sure that when we send the traffic, instead of over the link protected, which has just gone down, to the backup router, that the backup router, or the alternate next hop, doesn't send it back to us. So if the link goes down towards the destination, we can safely send the traffic to B. B doesn't forward it back to us. That's all we need to do. Router A needs to find an alternate next hop. No signaling protocol, Nothing like that. Everything is local to router A. He does all the calculation. He stores everything in the routing table, ceph table, and so on. Right. Now we're going to... A question, yes? Yes?
Does it make a difference to protect the links? But what happens if the router is down instead of just the link?
Good question. I was coming to that, but why not let's answer that now. So I'll paraphrase your question. Router A sees the link going down, but maybe the node is down. How will router A know? It doesn't. It just sees the link go down. It could be two events. Now, it's up to you, the operator of the network, to do something about that. There are a couple of things you could do. First, we will see later LFA can do node protection. That means the backup path will not be through router C, the router at the other end of the protected link. You can do that. It's not on by default. You can configure it. Or you have a nicely developed network. All the routers have active RPs, backup RPs, NSR or NSF. All the power is backed up. Then the chassis will never go down completely. And then you don't care about node protection. So that's your choice. All right. Now we're going to split. First link state, then only a few slides on EIGRP. Link state protocols, they build a routing table from the database. In between, we have an SPF or Dijkstra calculation. We need to find the shortest path from any router, or the router calculating, to every other router. And the prefix is attached to it, of course. So we have a nice network here with the cost of the links on it, of course. We are now router A. We are going to calculate the routing table, be it OSPF or ISIS. So we run SPF, shortest path first. Now, we are router A, so we are both the calculating router, but we are also the root of the tree. There is a tree from me, router A, to everybody else. So I'm the root router as well. I do the calculation, and I find a single path, if there's no ECMP, to every other router, and the prefix is connected to that router. And it will look something like this, a tree. Fine. This has been going on for more than 20 years with link state protocols. No issue there. This is not LFA, this is regular SPF. Now comes the trick, only for link state protocols. We still have the same topology. We are still router A, but now we are doing calculation for somebody else as the root router. In this case, router C. So we are going to behave as if we are router C and calculate the topology from router C to every other router, including ourselves, router A. Why can we do that? Because it's inherent to link state protocols. Link state protocols always have a database. It's within one area or level complete. So you can act as if you are any of the other routers and do an SPF from that viewpoint. No issue. So we can do that. That's a special SPT or SPF. We call that a reverse SPF. So somebody else is the root router. I'm still the calculating router. So this is the trick we need for LFA, link state protocols. However, you might say, look, I have 2,000 routers in my area. That's going to be a lot of calculation. We could have done that. We didn't do that. What will make it work is that router A will only have to run one RSPF per neighboring router. Don't tell me your router has 2,000 neighbors. Maybe it can, but, right? So that's okay. It's a lot less routers, a lot less calculation for router A to do. Yes? Yeah. So if you have 2,000 neighbors, yeah, but it will be a lot. Now, it's still not an issue because it's never a high priority, so executed as high priority process. Everything else, the regular SPF takes process. But if you have 2,000 neighbors, I would assume you have like a DMVPN network or something. Oh, sorry, yeah. So what is the issue? Yeah. So 2,000 routers is a lot. Now, some are getting close to that. But if you run a few SPF, it's fine. So if instead of running one SPF, you have to run 10, it is fine. And other processes will take higher priority, right? But it's better than running SPF 2,000 times, right? Yeah. Of course, there's a little bit more work. So I'll come back to that. When the special SPF, fast reroute SPF, runs, it's like a background process, and it can always be interrupted by some other process. So it's not really an issue. It's not another thing to calculate. We're only calculating backup paths. Some definitions. We'll also always look for the calculations from the standpoint of S, the source router, towards D, a destination router. Right? Primary next hop router is router E. I don't know why it's E, but it's used everywhere. Fine. And then we evaluate alternate next hop, neighboring routers, router N, if that's a possible LFA or so alternate next hop or not, right? Yeah. So the primary here, possibly an alternate here. And also we have the notation distance A to B. Now distance is metric or cost is not admin distance from, so the shortest distance from router A to B or node A to B. Right. Most important slide of all of them. Now, by the way, you can see there RFC and you will see one more. Okay, there are a couple of RFCs describing all of this, but to be honest, all of this happens inside one router. So basically, we, Cisco or somebody else, could do what they want for LFA, as long as it works. Like I said, there's no signaling, no packet format, so the RFCs are what they are, but we don't need to talk to a router of another vendor, so we basically can do what we want. Most important slides. What are the rules or inequalities? So first of all, if in our network we want to have loop-free alternate, then for the next hop under investigation, we must make sure that the cost from N to D, this one, is smaller than the cost from N to S plus S to D. Basically saying, S, if we send traffic to N, he's not going to send it back to us. That's it. And that's the basic algorithm for loop-free alternate. If you have this, then you have an LFA. You're good. If we want to be a bit more strict, we can say, what's the definition of a downstream path? Well, if the cost from N to D is smaller than the cost from S to D, obviously N is closer to D than S. So N is more downstream than we are. The only advantage is that in the event of multiple failures, multiple links going down, you will still have protection. Where is this used? Long time already? Yeah, enhanced IGP, right? Feasibility condition and so on. By the way, this is the same as this, but with distance NS being 0. And then finally, node protection. Well, what gives us node protection? If the cost from N to D is smaller than the cost from N to E plus E to D, then we know that when we send traffic to N, it won't go through E. So, to the question, you will have to configure something, a keyword, and then we evaluate inequality number 3. Now be careful. You can configure this, you can configure this. The more you configure, the more strict you want to be, the less coverage you will have with a regular LFA. It's a very important slide. And the most important one is the first inequality. One more thing. What do we have here, which is special? A broadcast segment. A VLAN, Ethernet, SVI, whatever. If you look from S to D, the primary path will be this, over E. If the link fails here, then S will reroute to N. But what does it mean again if the link fails? It could mean that maybe there is a catalyst here which supports the VLAN. It could be that only this segment is down, but it could be that the catalyst is down, so the whole VLAN is down. So we must avoid that even though we send the traffic over the backup path to N, it doesn't backflow like this and then go to the destination. That's what we need to avoid. That's only specific for broadcast segments. And we do this by imagining there's a pseudonode router here, and not a real router. This router represents the segment, the VLAN, and it has a cost of 0 out of all interfaces. The rule is now, the inequality, the cost from N to D, if that is smaller from N to this pseudonode plus the cost pseudonode to D, then we're good. Then the traffic will not backflow. That's inequality 4. Are we good? Some examples. I always like examples to make things clear. So we have the same routers again, SEDN, and the cost of the link on them. So what do you think this is? Do we have LFA here? Well, N to D smaller than N to S, S to D, yeah, it looks fine. To remember, here it is. What about downstream? N to D is smaller than S to D, for sure, 11. Node protection, N to D is smaller than N to E. That's the smallest, shortest path, and then plus the cost E to D. I'm guessing this is fine for all three equalities. And here it is. All three are good. That's not necessarily the case. So try to keep more or less the same topology. We just changed the metric here, and you can see we still have LFA and node protection, but it's not downstream anymore. And you can see that, right? N to D is now 20, but S is closer than this 20 to D. It's not downstream. Can get worse. Intuitively, you can see now that we don't have node protection. From S to D, we go like this, but N, when he needs to go to D, he would go through E. There's no other way. Even if it would be this path, it would be through E. So in this case, there's no node protection. It's still LFA. The first one is still okay. Because N is closer to E this way than this way. This is 20, this is 22. Still LFA, no node protection. It's obvious. A couple more examples. We increased the cost on some of the links here. Strangely enough, it's even downstream, but still not node protection. Last one, nothing. There's no link here. This link has such a high cost, it's higher or just equal than this cost, so no LFA at all.
What's the impact of not having downstream?
So more or less the only thing is that what's the impact of not having inequality 2, so downstream path? It protects against all kinds of events, so multiple events at the same time. Very important. And LFA, we protect something local, I'm S, and I protect this one link going down. What do we not protect is this link going down at the same time as another link somewhere else. Because that link somewhere else might be on our backup path. And then finally, an example for the fourth inequality. So we have this broadcast link. Primary path is like this, through E on the bottom. Backup path should go to N, and then, well, this is 25, and this is 10 plus 11. So it will go like this, backflow over this segment. So this is not LFA, if you do the calculation. Good? A bit more theory. Now, there were two big ways to do protection. We can do per link or per prefix. What does it mean? Per link, it means we try to protect all the prefixes over that protected link in one shot. So we will move them all together, but all to the same alternate next hop. With per prefix, we say, no. We are granular. We look at every prefix, and we calculate, perhaps, a different alternate next hop for each of those prefixes. Let's look at the advantages and disadvantages later, but first have a look at some examples here. So, protecting this link, what if we have two destinations now, D1 and D2. What if we pick this one as a next hop? It works. But with per prefix, we could be more granular. We could pick N1 as an alternate next hop for D1 and N2 as an alternate next hop for D2. So prefixes can have different alternate next hops. With per link, it all goes to the same next hop, N1 or N2. We pick one. All right. So one of the disadvantages already is obvious. All the prefixes, all the traffic will now go this path. So you cannot spread them out, right? More. What about the coverage? Let's imagine now we have two prefixes here. One is actually connected to D and one is connected to E. So for the prefix Y, E becomes also D, the destination router. What do we have? First inequality, that's what we care about right now. So for X, the distance from the backup next hop, 15, N to D, is that smaller than the cost, wait a minute, N to S, yes. N to S plus S to D. Yes, so we have LFA for X, but we do not have that for the prefix Y, right? Because this link has a very high cost, 20. So no LFA. Remember what we said, it's for all prefixes, the same alternate next hop. If you have 100 prefixes, one of those prefixes is Y, so it doesn't have protection. None of them have protection. Here we changed the cost to something higher. Now this cost becomes relatively lower, and we do have LFA protection now for both X and Y, because this has increased. So now we can protect both of them, and the next hop will be router N. The alternate next hop will be router N. So what is the conclusion? Per link, it's all or nothing. You can protect, you find an alternate next hop for all your prefixes, fine. There's at least one. No protection, none. No protection for any of the prefixes. Right? And that's why it's not really recommended to do this, right? By the way, only iOS XR does that. Node protect, sorry. Per link protection. iOS doesn't do it, right? But iOS XR and iOS do both per prefix. So no issue there. And that's the most advisable thing to do. One more limitation. Let's have a look what can go wrong. Again, two possible alternate next hop. So this is a protected link. What if we pick N2? Well, that's going to be a good alternate next hop for the traffic to D2. This is 50, much smaller than all the other possible paths. But towards D1, this is 60. So this path, 51, is going to be shorter. So the traffic is what? Is looped back to S. So for D1, N2 cannot be an alternate next hop. So if you do per link, then prefix D2 also does not have an alternate next hop. Let's assume it's N1. Well, for D1, that's good. This cost to get to D1 is still 30. But now to get to D2 from here, from N1, that's 100. That's 100 as well. So this is going to be the lesser 81. Yeah. Okay, but then N1 sends the traffic back to S for destination D2. Again, for both prefixes, no protection. So it's all or nothing per link. Meaning that in many occasions, depending on how your network looks like, and I'll talk about that a bit later, you might not have protection at all. If you have a fully meshed network, you might still have a lot of protection with per link. It depends. And I'll give us some examples of topology later on. So, per link versus per prefix. First of all, in XR, you can do per link. So you can actually choose, on one router, on this link, I'm going to do per link, and on another interface, I'm going to do per prefix, and yet another interface, I do per link again. Wow. It's going to be difficult to manage and track, right? So that's probably not advisable. So probably per router, you choose per link or per prefix. In iOS, no choice, it's per prefix. Nothing else works. Advantage, disadvantage? Well, per link, it's simple computation. Only one RSPF for the router, the neighboring router on the other side of the protected link. But as we said, it's all or nothing. And the coverage can be low, depending on how your network looks like. Per prefix, there's a lot more computation to be done, because each prefix can have a different alternate next hop, many more RSPF for each neighbor of the S router, not just the neighbor on the other side of the protected link. The coverage should be much higher. Something about calculation and memory. So calculation, we already touched it a little bit. We have the regular SPF. It's always been there for link state protocols. We now have what we call an IP fast reroute SPF, both iOS and XR. And this is the process that calculates the backup path. It always runs a bit after the regular SPF if there's a topology change. And it calculates the backup paths. In the case that this fast reroute SPF is running and suddenly there's a topology change, a link goes down or up, a router comes down or up, then this process does not have high priority. It will be suspended and the regular SPF will run. Because any event that happens, link down, link up, is important and needs to be run first. Right? Calculating backup routes is not that important. We can do it a bit later. And then probably after that, we can resume the suspended process here. So CPU, yes, a few more milliseconds used, but not that much. Memory-wise, well, remember what I said. LFA is only there for IGP prefixes. We only need to calculate backup paths for IGP prefixes. I don't think anybody has 100,000 or 1 million IGP prefixes. BGP, maybe, not IGP. So if you have 100 or 1,000, whatever, we have to install an extra path entry for that one, a backup path for each prefix. The routing table, in the local routing table of the routing protocol, I'll give you some examples later. Every routing protocol has a local RIB, and in the Ceph table of the forwarding table. So it doesn't use that much extra memory or TCAM space or whatever we have in hardware. All right, so first time we actually look at some output. Pre-failure, what do we have? We have normally in the local RIB of OSPF, we see that here. So when OSPF runs SPF, it tries to build a routing table, right? But first it puts the routes into a local RIB, which is full of routes, only OSPF. No other protocol puts routes there. And then from there, we put the routes into the regular routing table. But you can see that now we also have a repair path or a backup path in the local RIB, and in the routing table, and in the Ceph or FIB table. If LFA works, then you will have a backup path. At the time of failure, so when the link goes down, we should have BFD. BFD will tell OSPF, do something. Right. But more importantly, at the CEF table, we will immediately switch over to the repair path that we have here, obviously removing the primary path for all prefixes at the same time. After that, maybe a few seconds after that, we have the regular SPF, and then we put the same or a new entry, post-conversions entry into the routing table and CEF table for the forwarding. But this is something we usually do not care about. Questions on this, routing table, CEF table? MPLS. So do you need MPLS? I already mentioned it in the beginning. No way. You don't need MPLS. Not LDP, not segment routing, not traffic engineering. You don't need it. If it is running, fine. Right? Your traffic can be labeled. We can protect labeled traffic with LFA like we do for IPv4 and IPv6. So for example, you could have an LSP labeled switch path through your network, and then this link could be protected by LFA. And all the prefixes, hopefully, are protected through the alternate next hop. The only thing that is a bit different here is normally in the IP table and the FIP table, you have IP prefixes. Now, you still have IP prefixes, but they have labels assigned to them. And each prefix usually has a different label, right? Obviously, if you do traffic engineering, it has its own protection. And in fact, you cannot do LFA for protecting a MPLS-TE tunnel. All right, so back to the coverage. We have an issue. Maybe my network has a certain topology and not every prefix is covered. Can happen, depends on the topology. A very nice example, and this is the worst example, is a ring topology. You can see it's not very meshed, right? There are no links in between, no diagonals anywhere. If you're a router S and you want to go to the destination, obviously this is the primary path. If it goes down, you have to go the other way. But if you send traffic to to R2, what will happen? It backfires, it will send it back to S and you have a routing loop. Temporarily. Until R2 converges. And that's important, right? R1 is closer to the event than R2. Sorry, S is closer to the event than R2. So he will do something faster than R2. R2 is a bit slower in reacting, normally. So you will have a loop, even though it might not be a very long loop, but longer than 50 milliseconds. So our LFA does not work. And everything we mentioned so far on LFA is actually directly connected LFA. We were the router, in this case S, the source, and our neighbors and our links connected to us. We didn't care about the routers out there in the world, right? So we call this directly connected LFA. It doesn't work in a ring. And it doesn't work in a square and things like that. All right. So what's the solution? Imagine that you are router S, and you could somehow magically encapsulate packets towards router 4. So force the packets on a path, this path, counterclockwise, towards router 4. Router 4 decapsulates and then forwards the packets still anti-clockwise towards router D. Because router 4 is now close enough, so there's no risk that 4 or 5 send the traffic back. Good. But you need such a encapsulation mechanism. You need a tunnel. There are a couple of options. The only one we implemented is the one with MPLS. And it needs to be signaled through LDP. It's not directly connected to S. There's multiple hops. So you need to have a targeted LDP session between the source and router R4. So we support only MPLS through LDP, nothing else. Right, so fine. It means you need to have MPLS in your network. But then you can increase your coverage. But how do we find or calculate the router 4? Where is he? Who is he? So here's what we do. If we are S, we need to protect prefixes over this link. S is going to say, well, who are all the routers, the set of routers, that I can reach without going over that link? Right? And you see them here in yellow. We call that the P space. The P doesn't stand for a word. It's just like in maths, a letter they picked. Router S also says, wait a minute, who are all the routers who can actually get to E without crossing that link? So we look at the problem from two sides. Right? From S and towards E. And we call that Q space. Doesn't stand for anything. Just P and Q are just two letters we picked. All right, now what? Well, we have some routers here overlap. They're both P and Q. We call them PQ routers. And you see we actually have 3 of them. Yeah, okay. We wanted 1, right? 1 is enough. We're not going to use all 3. So we're going to pick 1, and with the algorithm, the software we have, we're always going to pick the one which is closest to S. That one we pick, and then we build a tunnel, MPLS, LFA, towards that router. Problem solved. Yes, except that in many cases we ended up with something like this. And an example is a square where all the links have equal cost. No LFA, no remote LFA, no PQ route, no intersection. Okay. One more trick up our sleeves. Now, we're not just going to calculate all the routers we can get to from S, but also all the routers we can get to from the neighbors of S. In this case, the router N. There could be more neighbors, of course. The result of that is that we slightly increase our P space, like you've seen here. And now we might find one or more PQ routers. And now we pick one. Now we have the drop-off router, the PQ router. So now S can build a tunnel, MPLS tunnel, to one of the PQ routers. Okay. Is that clear, remote LFA? It's not on by default anywhere. You need to configure it. The good thing is, if needed, if you configure the remote LFA, then the extended P space is enabled by default. That you do not have to configure. You just need to enable remote LFA. So let's have a look at an example. Topology, 5 links. Red link is the protected link. First thing we do is, nothing new, regular SPF, and we end up with router A, calculating router, and the root router of the topology. We end up with this. Okay, remember P space, all the routers S can get to without crossing the link. Well, obviously, router C and E are reachable, but over the protected link, right? So no good. We have to remove those, prune them off. We are left here with router B and D, the P space. Easy example. Regular SPF. Router A does calculation, router A is the root. Now, for finding the Q space, we're going to use that trick. Remember the trick, reverse SPF? Router A is the calculating router, but now the root is the router on the other side of the protected link, router C. So reverse SPF, A is calculating, but C is root router. All the set of routers that can get to C, not crossing the link, D and E, but not A and B. So those two need to be pruned off. We are left with a Q space of 2 routers, D and E. Next step, we have P, we have Q. PQ. Find a PQ router. Well, the yellow and green, we're going to look at them here. Right? Do we have intersection? Sure we do. It's router D. So in this case, we only have one PK candidate. Could be more, but we only have one. So that one will be the endpoint of a tunnel from A to D to protect prefixes connected to C over the red link when it goes down. Let's have a look at the packet forwarding. The packet forwarding, we have MPLS, so let's see what happens. The same topology. Now we have a prefix X connected to the destination here. We find a PQ router. We've seen it on the previous slide. We build a tunnel. How do we build a tunnel? With LDP. Targeted LDP. Now, what does it mean? Targeted LDP. That's not enabled by default. You have to enable it. There are a couple of ways to do it. Most people just enable the acceptance of targeted LDP. I think it's on the next slide. So we have a tunnel from A to D. We have an LDP session over it, targeted. So now, router D, the PQ router, will send all its prefixes with a label. He will send label bindings, including the prefix X and a label 99. So now when that link goes down, instead of forwarding the traffic A to C, the traffic will be forwarded A to D with an extra label, MPLS label 99. The packet is forwarded, we have penultimate hop popping, and then the packet is forwarded with whatever regular label towards X. So this is how the forwarding works with remote LFA. You do need MPLS enabled in your network. You do need remote LFA. Sorry, MPLS and targeted LDP session. One thing, remote LFA has a sense of direction. Imagine this network, it's getting a bit more complex. We protect this link, and you see the cost of the links here. Can we find a PQ router? Well, kind of yes, this is the C router here. But yeah, wait a minute. To get A to C here, that's a cost of 200. So the best way is this way, right? 1, 1, it's 4. That won't work, right? Because when that link goes down, the tunnel is kind of over the protected link. So the tunnel would fail at that moment. Now, wait a minute. In software, we're going to say, no, we're going to force that tunnel over this link to the C router for protecting every prefix over the red link. So the tunnel, the LFA remote tunnel, has a sense of direction. It's going to point out this interface. And we can see that. This is output from iOS. The same is there in iOS XR. When you look at the local RIP of OSPF, you see the primary prefix. The repair path points to the PQ router C. And it has a special virtual interface, MPLS remote LFA. So these are remote interfaces. Each virtual interface represents a remote LFA, a tunnel. And you can see it points with a cost of 203. This is this path. And it is next. If you do show IP interface brief, you can see that it's linked to this IP address to this interface. So that's how it works. Even though the tunnel is not going to be over the shortest path. So this is something that you should know. Let's have a look at topologies and coverage. So triangles are nice. You'll have LFA all the way around. If what? If you're not very adventurous and the cost of the links are more or less the same everywhere, or the same, then it's all fine. You just have normal, regular LFA. Inequality number 1. In a square, you don't have LFA. Not possible, because if you look at the alternate next hop, router C, to get from router C to B, you probably have an ECMP, equal cost path, to B. So it's not possible. You could go back to A. There's a chance. It's equal cost. Even remote LFA is not possible. But remote LFA with extended p-space is good. Okay. So squares, every link the same cost, remote LFA is good. Pentagon and anything more, well, then it becomes a ring, I guess. No LFA, but remote LFA is possible. So LFA, and certainly with remote LFA, you have a lot of coverage. Everything? No guarantee. Because if you are adventurous, you will play with cost. You're going to say, from this city to this city is a low cost, but through the other path is a high cost, so I increase the cost of the links. Everybody plays with link costs, so you could have that. So let's say on a triangle, you increase the cost here of one link, it has an impact. If you look at router A, well, let me tell you what happened a few weeks ago with a customer, and they opened the attack case even for that. When you look at router B being the source towards router C, then yes, router A is an alternate path. So they set up a network of 3 routers in the lab with a traffic generator, and they drop the link, and then they see reroute, everything is fine, perfect. A few days later, they test, they put the traffic generator here towards the destination, they kill the link, doesn't work. Okay, they forgot to check they had actually a backup path or not, they don't. And the reason was the cost of the link was so high. So it also depends from where you are looking, that's my point. So always keep that in mind. Right? But the point here is, you play with metrics, you're probably going to have less coverage. So no LFA, no remote LFA. From A, you might have it from B to C. In a square, again, one link has an increased cost, no LFA, no remote LFA. Even worse, you start playing with asymmetric link costs for whatever reason. I do not dare to ask why you are doing it, but some people do it. So you have a different cost of the link on either side, right? Well, because now from C to B is a cost of 100, there's no LFA, no remote LFA. Yes?
Well, that seems to be quite complex to build all those targeted LFA sessions. If you have a high number of routers, are you looking into using segment routing? Build those tunnels?
Okay. I'll paraphrase the question. I think that's already two questions. You have a lot of, if you do remote LFA, you have a lot of tunnels to build to different routers. And then you said something about, what about segment routing?
Yes.
Okay, so you can have a lot of tunnels, remote LFA tunnels. Now the point is, you might already have them if you do pseudo wires and VPLS and all those kind of things. You might already have a targeted LDP session. One targeted LDP session from one router to another is enough. You don't need to build extra ones. So if you do have one already, that's good. We can reuse that targeted LDP session tunnel also for LFA, besides using it for pseudo wires and whatever. Right? To your segment routing is special. Very nice, but special. And we come back to the protection on segment routing more or less the last section. All right? That's a different beast. A square, again, no protection. Okay. So we are stuck. No protection? Well, yes, there is. There's always yet another trick up our sleeves. All right? We could have done something which is on the next slide, but the real solution is actually what just has been mentioned, is segment routing with TI-LFA. That should give you protection always. But you have to have segment routing. There's always advantage, disadvantage. Ascending cost, you see, we go to a higher and higher cost. Can we have protection here? Because whatever your router you pick, so regular LFA to C or remote LFA to D or remote LFA to E, the way back is always smaller than the way upstairs. No protection. We could have done something. We could have said, what about a remote LFA tunnel to E, and then we make sure that E forces the traffic out, like with an MPLS label, forces the traffic out on the next link to the destination, to router B. We call that directed. We could have done that. It would have worked with remote LFA. We didn't. Because we're going to do this trick, kind of, for segment routing, so with TI-LFA. Okay. There we have this kind of behavior where we kind of tunnel the traffic and then direct it out to the next hub. More on that later. A couple of examples here. Backup path versus PC path. Remember I said the backup path is not necessarily the PC path. Here's an example. If you enable node protection, then this cannot be the backup path, even though it's the PC path, but the backup path is this one. It's still an LFA, this path. That means link goes down, traffic goes to D, in 50 milliseconds, and then, I don't know, a second later, regular SPF, traffic switches to C. Is it bad or not? Well, the traffic moves once more. It's not that you're going to lose traffic. That's probably not going to happen. But what you do have is you might have a lot of traffic moving and moving again, and it might be too much on a certain link. That's the point, or path. So here's the example, right? Because you have no protection on, and this path has no protection, the backup, this one doesn't, we choose the one with a higher cost. That's what it is. Another example. This is the protected link. The backup path is not the second best. It's kind of the third best. What do we see here? Is D an LFA? No, because if A sends the traffic to D, he will send it back. This is 3, this is 10. C an LFA? Yeah, but this path is 12, this path is 11. So the LFA is not the second best path. This is the LFA, but after the event, after regular SPF, this will be the PC path. You can always check that in your local RIP, how the repair path looks like exactly. By the way, these are kind of slides I made after some cases and after we explained a few things to customers. That's where the ID comes from. This one as well, customer couldn't figure out why this PQ router and so on and so on. Why is here the backup path not on the post-convergence path? Let's have a look. There probably could be 2 PQ routers. This one, yeah, for sure. Why C? Well, if you look from A, C is closer than D. Remember, we picked the closest PQ router. So the tunnel will be here. Packets are decapsulated towards F. But then, after regular convergence, this is the PC path. Not always easy to understand. So we had a tech case about this. We had to figure out why this was happening, because again, we had a lot of traffic moving and it caused a problem for a short amount of time, because this link couldn't handle the traffic. Another note on microloops. We are getting closer to the end of the theory, by the way. Protect this link with a remote LFA tunnel. That's fine. So if the link goes down, we switch all the traffic in 50 milliseconds over the remote LFA tunnel. It works. And then we have seen with a few customers, LFA works when the link goes down, and then something fails a bit later. A few seconds later, a minute later. What's going on? In this case, a few seconds later, S was a very fast box. No names. I want to protect the innocent. N was a very slow box. No names. I want to protect the innocent. And S did a regular convergence faster than N. So when S finished its regular convergence, somewhere around here, well, it depends on which prefix, but somewhere around here, it started sending traffic to N natively, not on the tunnel anymore. No LFA, just plain. N, very slow, still updating the routing tail, the line card, was behind, right? And he still thought the best path was through S. And then he sent the traffic back. Micro loop for maximum few seconds. Solution, very simple, just delay the switching over from sending the traffic over the tunnel to natively sending them to the new primary next hop router N. Right? So we're just going to delay that. And the default delay is 5 seconds. You can change it, but that's a default delay. The command is later in the next section. That was most of the theory. You still have doubts? You can go on. Yes, sir. No, I cannot hear you. Hold on.
Slide 40, if I was running ERGRP, what would you prefer, the LFA or the feasible successor?
If I was running ERGRP, what would we prefer, the LFA or the feasible successor? We'll come to ERGRP after this section, but the question is, it's the same. Your feasible successor will be your LFA. And I'll give you an example. All right, configuration, implementation, and troubleshooting. Actually, I could have been short here. I could have said there's one slide. Look, there's one command. You enable this command, that's it. Maybe a second command for remote LFA, and that's it. Typically at Cisco, the easier to configure something, the more stuff is under the hood and make it work, right? So it's a bit like that here. One thing, we'll have attributes. What are those attributes? Well, let's say you're not just happy with any regular LFA, but you want node protection. That's an attribute. You want downstream path assurance. That's an attribute. Lowest cost. That's an attribute. Multipath, meaning if you have two paths, one path can protect the other, versus, no, I want an extra backup path protecting both the primary path. That's an attribute. All of that is something you can configure. We have a default set that we have configured, but you can configure it. There's also an order, a preference. One is preferred, looked at before the other. We do that by looking at a certain preference number. And like I said, everything is configurable. The one thing you need to know is, as soon as you configure one attribute, we clear all of the default ones. So if you want multiple ones, you have to configure all of them. Not think that the defaults are there. You configure one, they're all wiped. So you have to start from scratch. Very important is this elimination rule. We'll go through all the attributes one by one. Do we have node protection? Do we have downstream? And so on. But let's say you go to all your possibilities, and suddenly you hit a check where do I have node protection? And none of the backup paths apply. Then you would say, no, I don't have a backup path. No, we don't do that. By default, we say, OK, then skip the rule and try to find another one. Right? That's the default behavior. You always try to find one. However, if the router, if you say, no, node protection is something I absolutely need, you can see you can configure that as a requirement. It must be node protection. No node protection, no backup. You can configure that. OK, so here are all the attributes that we have, iOS and iOS XR. I will not go over all of them. But the first one is shared risk link group. I think you know what it is. Somebody doesn't know what it is? So multiple links over the same fiber, sharing the same risk, right? Primary path interface disjoint, meaning backup. You want to make sure that your protected and backup is not on the same interface. Broadcast interface disjoint. I mentioned that already, and so on. Let's have a look at how this tie-breaking works. The example is OSPF and iOS, because it's the clearest to show. We look at the local RIP again. This is the primary path for this prefix over Ethernet 00. I enable the command, I will tell you later, but I see here all the possible backup paths. Which one are we going to pick? By the way, you see all the attributes there. Well, in OSPF, this is the default tie-breaking. All the attributes with a particular order. This is the example, iOS, OSPF. If you want it for ISIS or XR, it's in the appendix of the slides. So this is the set we are going to go through. OK, let's do it. SRLG, none of them have SRLG. Primary path, yeah, 2 and 5, don't have primary path in red now. So they're not good. Eliminate them. We still have 3 more. Then we look at interface disjoint. Yeah, path 4 doesn't have that. Why? Path 4 is on Ethernet 00. Well, so is the primary, so not going to work. Remove. We have 2 left, but all the rest is the same. So we go all the way through the end. We hit the load sharing. Now it's up to throwing the dice. We pick one of the 2. That's it. This case, path 1. And this will be the repair path put in the RIP. The others are marked as ignore. We don't use them. Remote LFA, I already mentioned that. You must have an MPLS network. You should have LDP and targeted LDP. So probably you need to enable targeted LDP discovery. So this is the iOS command. There is an XR command. And again, if there is already a tunnel from one router to another, we don't build extra tunnels. One is enough for all the services. Implementation nodes. Basically, a lot is supported. OSPF, ISIS, EIGRP, we are coming to that. But iOS, I already mentioned, doesn't do per-link LFA. And XR doesn't do ERGRP LFA, only iOS. The rest is kind of the same. Two quick, who does OSPF with multiple areas? Who does ISIS with multiple levels? Okay. If everything is inside one level area, it's easier for your link state because you just have one database. If you have multiple areas, you kind of have multiple databases. So in between them, you know, the areas, levels are stitched together through distance vector behavior, not link state behavior. So protection is a bit, well, we have to be careful. This slide and the next two slides, let's be quick about it. You have to know that both for OSPF and ISIS, any kind of prefix, let's say an intra-area or an inter-area, or if it's ISIS, the same level or a different level, can only be protected by another path of the same kind. So intra-area OSPF with intra-area OSPF, level 1 ISIS with level 1 ISIS. Done. That's what you need to remember. All right. Configuration. Very simple. There's only one command. Fast reroute per prefix, you enable it per area or globally. In iOS, you might have to configure it on every interface under router ISIS, but there's one command you must configure. Optionally, you have a few things. You could say, I only want protection for the /32s. Why? /32s are important for your service. If you have an MPLS VPN network, /32 is the loopback of the remote router, and that carries a lot of services. MPLS VPN, layer 3, layer 2, whatever. So you might say, I want to protect /32s only. Most people are okay with that, so that's the default. If you say, no, I want to protect also the /24s, you can enable that. So you can change this with a route map, iOS, RPL, route policy language, and iOS XR. You can change the tiebreakers in order, or just add, delete tiebreakers. You can say one interface, I don't want any kind of protection on that. That's fine. You can say another interface, I don't want any, I never want it to be used as backup for any other prefix. That's fine. You can exclude it. Remote LFA, not enabled by default, so that's something you would have to configure. And finally, you can configure the maximum cost to remote LFA. This is OSPF. ISIS is actually exactly the same, so I will not go over them again. The exact same options you can configure. Let's have a look at OSPF, iOS again. iOS XR is very similar. First thing is this kind of mandatory command, fast reroute. You enable it for an area or multiple areas, with or without external prefixes and so on. By default, high prefixes, you can do low as well. If you do low, it's the non/32s as well. And you can change it with a route map, it's iOS, if you want to. What about the options? This is the command to add a tiebreaker. You can say it's required or not. Required means, let's say, node protection. If I don't find a backup path node which gives you node protection, then I don't want a repair path. No good. Do something else. If you don't say required, okay, you go through the paths, none of them has node protection, you move on and try to find another one which is more or less okay. And the index is the number, the priority, so the preference level. One thing to be careful about, the implementations can be a little bit different. We have diversity here. So iOS typically goes low number to high for the preference, and XR the opposite way. These are the attributes for OSPF. And this is an interesting one. This is the command I used before. If you enable this command, then we keep all the backup paths, possible backup paths, in the local RIP. Why? Only for you to look at them, so for troubleshooting purposes. Normally, we only need one backup path. But now we store all of them so that we can look at them. And this is one command that I used like 5 slides ago to show all the possible backup paths. So some more commands. This is how you disable protection on an interface. This is how you disable an interface to be a candidate for repair paths and so on. Remote LFA, this is the command. You enable it in an area. Of course, you must have MPLS already enabled. And you must make sure you have targeted LDP sessions. So this is a common mistake. People have MPLS. They enable LFA, but if you don't enable the acceptance of targeted LDP, it's not going to work. Even though in control plane we say we found an LFA, if you kill the link, the LFA is not going to work, right? Yeah, and a maximum cost to the PQ router. For your information, these are the tiebreakers, and which are configured default and the preference, low to high. Some of them we disable by default, like downstream and secondary paths. We think they're the least important. So here's an example of everything you could configure, basically. SRLG, you typically configure on the link, and you do the shared risk link group. Somebody asked last time, yeah, but this SRLG gets, flooded throughout your domain. Not by OSPF. Well, we do now, but in the past we didn't. It gets flooded if you have traffic engineering. With traffic engineering, SRLG is not necessarily something local. With LFA, LFA is local. So the SRLG is local. So we compare this group, number 100, with other SRLG groups on the same router, not from somewhere else. Right? By the way, so far, we only talked about local protection. I'm a router, I see my connected link going down. I don't care about a link somewhere else. I need to do the protection. So these are the commands to disable protection, disable the candidate for repair, a route map if you want to change to do not only the /32s, but like in this case, /30, 31, 32, and then the other commands. Changing the attributes, keeping all the paths, and so on. ISIS, similar commands. Again, the configuration should be simple. By default, and that's what most customers do, they just enable fast reroute, right? So this command, and that's it. Any questions on configuration? Kind of straightforward. Troubleshooting. There are a few things we can check. There's only one or two things important. A command, similar command, exists in iOS just to see if it's enabled. Where is it enabled? Which area? Is it enabled for externals? What is enabled? Just LFA or also remote LFA? Is it enabled for the /32s, the high prefix, priority prefixes, or all of them? That's what you can see here. And then the tiebreakers. The most important command is the coverage. How many prefixes, or actually paths of prefixes, are protected out of any given interface on that router? You can see that in absolute numbers. You can see it in percentages. So if it shows 0, 0, 0 everywhere, then you did something wrong, probably. Obviously, the goal is to get it as high as possible. That kind of depends on the topology of your network as well. And then the second most important thing is just actually verifying in the tables if you have a repair path. The routing table shows it with an RPR or repair path or backup path, which IP route specific prefix as well. You see it in the local RIP of OSPF and ICS with more detail, the tiebreakers and so on, remote LFA information. And then finally in the CEF table, FIP table, you also have a repair path. Minimum information, outgoing interface, next hop. We don't need more. If it's remote LFA, also the label of the PQ router. For remote LFA, so that was LFA. That's all you need to do. This command to check the coverage, and then show IP route, the local RIP, show IP CEF. You're done. With remote LFA, there are a couple of steps. First of all, you verify, do you have a repair or not? If you don't, stop here, you need to figure out what has gone wrong. Then you verify, is there a PQ router? Per prefix, there can be only one PQ router. We don't do multiple backups anyway. And then you can figure out that virtual interface, the tunnel, where it is tied to, which outgoing interface. Remember I said a remote LFA tunnel has a sense of direction. Show IP/OSPF fast reroute remote LFA tunnels, more information. You see who the PQ router is, and you see what interface is protected on this box by that tunnel, and what the tunnel metric is. Most importantly, what most people forget, do I have a targeted LDP session from me to that PQ router? So do you have a neighbor, an adjacency, and a discovery? Transmit and receive targeted LDP hellos to and from the PQ router. Finally, what could still go wrong is we have a PQ router, we have a tunnel to the PQ router, but we are not getting a prefix. Because beyond the tunnel, we still need to forward the traffic labeled. So when we look at the binding on the calculating router, for that PQ router, for that prefix, we need to get a label. And in the repair path, we need to install that label. When we switch from primary to repair path, this label needs to be pushed extra into the label stack. Remember, I gave an example on this. So while repairing, you probably have two labels for the traffic. There are some commands for debugging. Again, this is OSPF iOS. Other commands exist for ISAS and iOS XR. This is a very interesting one. This is a very interesting one. So this is the RIP of OSPF for fast reroute, and this is the calculation itself. Both are very chatty. Never turn it on a real network. But probably a good piece of advice is when you want to deploy LFA, please go to a lab first and test it with traffic. Yeah? Think of what kind of topology do you have. Do you have triangles, squares, rings, whatever? What to enable? What is the cost on the links? Configure that, test it with traffic. How do you test the link going down? What do you do in the lab? Or what do you not do? You don't do a shutdown on the interface. Sorry? Yes, pull the cables. It doesn't matter. Pull the cable of the link. That's what happens in real life. Pull the cables of the power. That's the only thing. All the rest you should not be doing. Right? People do a shutdown, whatever. Okay. Some platforms, the shutdown will take, of an interface will take a minute or whatever to react. Some people restart an OSPF process or something in iOS XR. Those are all not good tests, right? So pull the link, be it the real interface link or the power cable. And please do it on real routers. There's no point in testing LFA on virtual routers, in VERL or on the UCS. That's just control plane. Doesn't work. Okay, so this debug, if you turn it on in a lab, this is kind of the output that you will see. I've removed some stuff. But you see that, for example, we start, well, there's a regular SPF. We don't care about that. And then we say we're going to schedule an IP fast reroute. You can see that. And then we're going to do reverse SPF for every neighbor we have. Remember all the theory we talked about? A reverse SPF for a neighbor. Not for every router in the area or level, but only for our neighbors. And then we try to find LFA. What if we still don't have LFA? Well, we are going to schedule remote LFA and do the calculations for that. So P and Q space calculation. We still don't find a neighbor. We do the extended PQ space calculation, which is enabled by default. In the end, hopefully, we find one or more PQ routers. We pick one, the closest one to us, calculating router, and we say, okay, that's the one. Let's create a tunnel. So OSPF, in this case, tells LDP, create a tunnel, if there isn't one already. If there is one already, a targeted LDP session, then we are fine. No need to create an extra one. IOSXR, well, if you just do show route there, you kind of see something interesting. These days, you have your paths with a metric, whatever, but you also see repair paths. They're all marked with exclamation, both in the RIB and in the LFIP, where we forward label traffic. And just a quick note, people asked about this, even open tech cases. Yes, the backup path has a metric 0. We just didn't care, and they put metric 0, right? Because, to be honest, we don't care about the metric of a backup path after we installed it in the routing table. And then there's also the global command, show OSPF, for example, to check what is enabled, which tiebreakers, and which preference. Note, like I mentioned already, here the preference in IOSXR is high to low. So the opposite of iOS. Coverage in OSPF, IOSXR doesn't show that much, but it kind of gives you a brief overview of how many prefixes paths are covered and how many those are in percentage. So that's always an important command to use in the lab or in the real network. Also, in the local RIP, for example, here in OSPF, we can look at the local RIP OSPF, specify backup path, and then you see the prefixes, path, and the backup path with all the attributes. For example, you could configure something like downstream protection is there, then this attribute can probably be used, right? The same for node protection and so on. Roundup, there are a couple of things you need to do. So there's a command, well, you have to do the configuration, obviously. There's a command to see if it's enabled, where it's enabled, which area, level, external prefixes, and so on. And then there's this very important command for all protocols, all implementations, to check the coverage. How much percentage-wise is covered, very important. LFA, of course, you need MPLS. Typically, you need to configure it, and then you need to make sure you have this targeted LDP acceptance command configured. And then you should be fine. And in the end, it just boils down to checking the prefixes and paths. So show IP route, show IP path, route repair, and then the local RIP and the CEF table. And the same, this is iOS, the same for IOSXR. No questions on troubleshooting? All right, EIGRP. It's going to be short. Enhanced EIGRP. Do we have LFA now? Yes. And why is that? Because we didn't have to do much. We already kind of had a kind of LFA for EIGRP, but in a control plane. The gentleman already mentioned, feasible successor, feasibility condition. EIGRP was built from day one with loop-free awareness. So it could switch from the primary path, successor, to a backup path, feasible success, instantaneously, without fear of looping traffic. That's there. Yeah, it's there. It's there in control plane. We didn't install backup paths in the data forwarding, in the plane, right? In the CEF or FIB table, there's no backup path. So yeah, it's a bit faster, but it's not fast enough. It's not 50 milliseconds. So in the end, what do? We reuse this feasibility condition, and if you enable LFA, it's not enabled by default, we make sure that the backup path, which will be a path through a feasible successor, is installed in the CEF table, and we have LFA. That's it. This is just an example on the feasibility condition. So first of all, the metric by default is the minimum bandwidth along the way, along the path, plus the sum of delays, right? From this message, metric, we calculate reported distance and feasible distance. Now, what are they? Well, look at the example. The feasible distance that we see here is usually the best metric from our primary path. And the primary path is always the first one we mention there. Okay. So usually this number is the same as this number, and that's the feasible distance, the metric of the best path. This guy is another neighbor in the topology database. Is it a feasible successor or not? Well, now we look at the metric, not through the router, but from the router. What did that neighbor report to us as a metric? Well, this metric, which is the reported distance, right? And now we compare it to the feasible distance. Is it smaller or not? Is it smaller? Then this guy is a feasible successor. As soon as it's a feasible successor, and you have LFA enabled, it will get installed as a repair path in the FIP or CEF table. So in the data plane. That's it. We didn't have to do much. It was just a hack in the CEF table. So an example of a topology, S and D, the source and destination. This is a primary path. The feasible distance is 200. We can see that. Are these feasible successors? Yes, because the distance 150 or 190 is less than 200. So either one of those can be used as an LFA. The other ones, not, because this cost is higher than 200. Not feasible successor, no LFA through them. And then the configuration is simple. Again, just to enable it, is this command. And you only have a few tiebreakers. For example, which one are we missing? I would think it's an obvious one, but because this is not a link state protocol, we cannot do node protection. It's a distance vector protocol. So there's no way to do node protection in EIJP. And then some debug commands. Any questions on enhanced IGRP? Straightforward. A lot of gain with little configuration. One command. All right. TI-LFA. So topology independent LFA. It is LFA, but here there's a big difference. We rely that you have segment routing. For example, with MPLS. Could also be IPv6, but let's look for now at MPLS. What is segment routing? And I try to summarize it here in one slide. I know it's not possible, but still, I have to start somewhere. So what is segment routing? We do source routing. We route from a source to a destination. And we force the packet to go a certain way. It's like traffic engineering. We do that by having the source router making a label stack with specific labels and a number of labels. And each label corresponds to a particular segment of the total path. And this way we force the traffic to go a specific way. But there are two kinds of things. We have adjacency SID labels and prefix SID labels. What are they? This is the new part of segment routing. Prefix SID labels are labels tied to one router and one router only. They're globally unique. You must make sure they're globally unique. This one router can only belong to one label can only belong to one router. Right? You have to configure that. This prefix SID belongs to this loopback, and it represents this label. And this is advertised by a link state protocol, OSPF or ISIS. So every other router knows that a particular label belongs to a particular router. That's prefix SID, globally unique labels. What do we use those globally unique labels for? Well, imagine that you are CE1 or P1, and you want to send a packet to P4. Well, then you're just going to have this packet, put a label stack on top of it with only the label of P4, the prefix SID label. And then the packet will arrive at P4. It does not change at every hop, like with LDP or traffic engineering. That's a prefix SID label. That's fine for getting packets towards a certain router. But what if you want to influence the path? then you might sometimes direct the traffic over a certain interface. Okay, we need something else. Adjacency SID labels. Those are labels tied to a particular interface. So that's how we force traffic to go over a specific interface. So let's have a look at an example. End-to-end service can be MPLS, VPN, layer 3, layer 2, and so on. But for the forwarding, let's take the example where P3 has the prefix SID label 16099 attached to its loopback. We have the adjacency label here 24001 for a link, and again a prefix SID label for a router 60007. Now we could force the traffic to go like this. Segment 1 to a router, segment 2 over a link, segment 3 to a router. Each segment is one label. So the packet we fire off from PE1 has 3 labels, tuk, 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 in the order of the segments. We do penultimate hop popping. So the top label is 16,099. It gets the label to P3. But because of penultimate hop popping, it arrives with label 24,001 at the top. We do a lookup in the LFIP and say, OK, we need to forward the packet over this link and remove the label. Packet arrives here at P6 with label 16,007. Do a lookup in the LFIP, OK, shoot it off to P2. And that's it. Source routing using label stacks. That's the thing we need to know of segment routing for TI-LFA. Because TI-LFA is the LFA for segment routing. No segment routing, no TI-LFA. To put it simple, it says here you can do link and node protection. You kind of can do everything with TI-LFA. Also, the coverage, as far as I've seen, is always 100%. Some of the concepts come back. For example, we can have this P and Q space again. We will create a segment to get to a router in the P space, a segment to get from a P to a Q router, and then another segment to go to the destination. What do you need to remember? To go to a P router, you need a prefix SID label. To go from a P to a Q router, you need an adjacency SID label. One hop. That's it. And a bucket path can be any number of segments. Usually it's small, no extra segments, 1 extra segment, 2. More is rare. I will show you an example. We kind of had a bit complex selection procedure for selecting the backup path. This was the rule or the set of rules. Forget it. What you need to know now in the later releases, I believe 6 and higher in iOS XR, it is just the minimum or the shorter list of segments. And that's it. Over the PC path. And that's very important. If you do TI-LFA, we can force the packets to go a certain way. We have source routing. So we can force the packets to go over the post-convergence path. Meaning, link fails, we switch the traffic on the backup path, and then we have the regular convergence, this traffic stays on the same path because the backup path is the post-convergence path. Let me give you a couple of examples. First of all right, we look from R1 towards the destination, route to Z. This is the protected link. But this link has a very high cost. How do we protect it? Well, intuitively, R1 just has to be able to send a packet to R5. They won't go back because the cost is so high. Every other link has a cost of 10. So just next hop. That's easy. So let's say we show the labeled packets. Here, R1, it just uses the prefix SID label towards route to Z. But if the link was up, he would also use that label to get the packet to Z. So when in protection state, we don't push an extra label. There's no extra segment. So we call that the zero segment protection example. This is like regular LFA we've seen before. Nothing fancy. However, all the links now have the same cost. We cannot just send it to R5, the traffic. If the link fails, R5 will send it back. We need to do something more fancy. We need to force the packets to go further. And it's a bit similar like with remote LFA, where we force the packet tunneled with MPLS encapsulation to a PQ router. We're going to do here the same. Not necessarily a PQ router, but it could also just be a P router. But the principle is the same. We are going to force the packets to go multiple hops and then remove a label, kind of decapsulate, and forward the packet onwards. So R1 does P and Q space calculation as we've seen before and says, well, if I get the packets to R3, we are safe, then R3 can just forward them onwards to router Z without looping, because R3 is also in the Q space. So what happens when the link dies? Now we still have this label to get the packet to router Z, but we push an extra label to just get the packet to router 3. One extra label, one extra segment. That's why we call it a single segment protection scheme. Right? More complex topology. This link now has a cost of 1,000, very high. P and Q don't overlap. What happened before? LFA? No. Remote LFA? No, there's no PQ router. Here, yes, we have a solution. We can bridge the gap here. How do we do it? First, we force the traffic to go to R3, then one hop to R4, a JCC seed label, and then we just send the traffic towards the destination. 2 extra segments. First extra segment to R3, second one to R4. So now we're going to push 2 extra labels. 17,003 to get the packet to router 3, and then the adjacency label here to get the packet across one hop to R4. 2 extra labels, 2 extra segments, hence double segment protection example. All of this is possible because we have a link state protocol, we have MPLS encapsulation, we have segment routing. That gives us topology independent LFA. Any questions on this? Configuration, really easy, but you must enable the regular LFA before enabling the TI LFA. I mean, you need to enable them both. You need to configure them both, all right? And you have TI LFA. That's the thing. If you forget the first command, it doesn't work. So both ISIS and OSPF example. There's one thing missing. The examples didn't show a network where we had asymmetric cost on the links. We are coming to that. Let me first show you an example, TI LFA. It's all iOS XR. This is my topology I used. What do we have? Well, first look at the first part. This is a calculating router. We are trying to protect prefixes connected to router B. Primary path, backup path. Will we have an LFA? Well, for sure. You would even have a regular LFA. So for sure you will have TI LFA. How does it look like? Show route. We see this link is protected. That prefix over that link is protected with this LFA towards router C. In the routing table, in the fast reroute database of ISIS, we see it as well with a little bit more information. And in the Ceph table, we have it as well. We actually don't push an extra label. This is just a label to get the traffic to router B. Very simple. 0 segment. 1 segment example. So now it's a square. We first have to get the traffic to router D with 1 segment, and then to router B. So the repair node, as you can see here in the routing table, is router D. In ISIS, we also see the backup path and the backup label. This is a new label, an additional label that needs to be pushed at the top of the router, of the packet. And we just call this node a P node. Now in all the software, if you go home and start some testing in 6.0 software, whatever, you probably still see PQ node. But now it's being cleaned up, and it's P or Q in TI-LFA. So, yeah, we still have this label to get the packet towards the destination, but we push this extra label. So this is an example of one or a single segment protection. Double segment protection. Rectangle, and one of the links has a very high metric. Remote LFA wouldn't be possible here. But with TI-LFA, we're now going to create two segments. So the first segment is towards router D with a global or prefix SID label. And then the second segment uses this label, adjacency SID label, which is a locally assigned label from router D to get a packet to router E. So we push two extra labels. It's a double segment protection scheme. And you can see that also in the CEF or FIB table, we push two extra labels. All right. What about triple segments? And now I did this weird thing where we still have this rectangle, but now we have asymmetric cost, actually twice. You wouldn't get LFA here and remote LFA, because if A starts sending traffic, it would always go back. Even if it reaches E, it always finds the better way is back instead of forward, because forward is always this high cost here in red. LFA, no. Remote LFA, no. TI-LFA, yes. But hold on. We just did it and we don't see here anything. In ISIS, yeah, I see the pushed labels, but in CEF, I don't see the pushed labels. So the routing table, no repair path. CEF table, no repair path. So actually, it doesn't work. Right? Even though ISIS tried, you don't have an LFA. You don't have a repair path. So what is wrong here? Well, it's not something you would know. But for this to work, you actually have to enable SRTE. So this is kind of the traffic engineering based on segment routing. And that needs to be enabled. It's pretty simple. It's this one command. And then our software, iOSXR, uses the autotunnels. Because if you need to push more than two labels, we need autotunnels from SRTE, from that piece of software. And then we will be able to push 3 labels or more. This is optional if you want to give your autotunnels a specific number range. Okay, probably makes sense. You can number them 1,000 to 2,000 here. So again, this triple segment. Interesting. So we did this configuration. We enable SRTE. Now we see the backup path is a TE tunnel 1000, which is used for SRTE. And it actually says local LFA. All right. In ISIS, yes, we push 3 labels. But in the FIB table, we now see, we forward towards a tunnel, right? SRTE. And SRTE will do that encapsulation, as we'll see on the next slide, of the 3 labels. So the 3 labels are bound to this autotunnel 1000. So the autotunnels are created on demand automatically by the iOSXR software. You don't need to configure anything, right? Just that one command. There are autotunnels, which we had before in our software. Questions? Yeah, so concerning MTU, what about the label stack SR? So there are 2 things, is how many labels can be pushed. Yes, it will increase your MTU, that's for sure. We have the same in MPLS networks forever. It used to be a problem like 15, 17 years ago, I remember. They kind of all have been solved on our routers. And the same for the MTU, really. I mean, it's up to you, right? But what you configure. But of course, if you go to your router and you configure an MTU of 1000, it's probably not going to work, right? But by the way, in real life, what you typically get is everybody at the edge, which is you people here on the Wi-Fi, you never send packets more than 1500. And whatever we have in the core is an MTU on the links, which is much higher. So usually you don't have a problem. I understand, it depends on your design. You can have problems. And if, of course, on top of that, you do whatever you want to do in your data center, like VXLAN encapsulation. Yeah. The more encapsulation, the more a problem it can be. You need to fix it. You need to do fragmentation, enable path MTU discovery at the edge, or fix your MTU issue in the core. Yeah. But that's a problem of any kind of encapsulation, right? Like I said, we've seen that in the past as well, with just regular MPLS VPN with 2 labels already. Yeah. But it's a valid point, it's something to watch out for. One more thing which TI LFA makes possible is microloop avoidance. And this is neat, this is really neat. Because for the first time, we're going to talk about something which is possibly remote. It can still be local, a link going down or a link coming up. It can also be remote. Very interesting. We are router 1. In this example, the primary path is here towards router 7. But if the link fails, if now we send traffic here, there is a possibility, don't look at the labels yet, there is a possibility that R5 sends the traffic back, if we send the traffic only with label 16,007 to get a packet to R7. Because maybe R1 converges faster than R5. And then we have a microloop. Not very long, but it is there. So how can we avoid this? Well, I've already shown it to you. We're going to do this. As soon as we detect the event, so router 1, he sees a remote link going down, he's going to run an SPF and say, get a packet path on the post-convergence and force the traffic down. How can we force the traffic? Make a label stack. Each label represents 1 segment. So do source routing. And then later still do the regular convergence. So there are 2 stages here. So the link goes down, we have a near and far router of the link. Traffic is forced with multiple segments, multiple labels through the post-convergence path. After regular convergence, R1 will just forward the traffic with the regular label stack, the prefix hit label of R7, and we are done. Link up, same thing. When the link comes up, R1 detects it. He will force the traffic over this path with multiple labels, multiple segments, because otherwise R2 might forward it back to R1 if R2 converges slower than R1. I know it's closer to the event, but maybe it's just slower than R1. And then after convergence, we send the traffic as regular, usually just 1 label. Okay. Just one thing, yeah, this is the command to enable it. Again, MPLS traffic engineering, loopback, whatever, you can change the numbers. This is what you need to enable SRTE. Remember we talked about microloop avoidance before and now, they're kind of different, right? So this is the old command for microloop avoidance. This is the new one for segment routing. It says segment routing. Again, 5-second delay, you can change it if you want. To see if it's running, show ISIS, show SPF, you see it's enabled where if it's currently active for a specific event and so on. I call the label, the routers near and far because that's actually what you see on the output of show commands and debug on the routers. Show ISIS SPF log now shows these special SPFs for microloop avoidance and for what event, a link up, a link down event and so on. And then finally, while a microloop is active, you will see in the FIP table that we push extra labels, like I mentioned. Debug TLFA, okay. You see the output there. Any questions on microloop avoidance? Not enabled by default. You can enable it. You need segment routing. And then the final section is on WAE mate. So WAE is the WAN automation agent. It used to be, well, mate, but now mate is part of WAE. Very important because when you play with LFA, be it regular LFA, directly connected, remote LFA, or even segment routing, you want to verify things. You might have a complex network, be it your real network or a simulated network. You can test that in Mate. You can see the prefix coverage, if you have LFA, remote LFA, and so on. So you can do a lot of modeling, testing, verifying there. You can get the information through SNMP and the config from real routers, or you can just put your fake network on there, and both can be verified. I gave a very simple example here, triangles, pentagon, square. You see triangle always have 100% coverage. You always have direct LFA coverage. A square is yellow because what? Because it's not 100% coverage. It's somewhere between 0 and 100. And obviously, if the link is red, it's 0% coverage. Yeah, there is no alternate path to go left, right here, so that's why it's red. But you see a lot more. Huh? You see directly or remote LFA, you see which PQ router was chosen and so on. So it's very nice to kind of, in a weekend, model your network there and try everything out and see how it behaves before putting it on the real network. Just one note, both for LFA, remote LFA, and for segment routing, you have to put in an add-on to do that emulation or simulation. We have 4 more minutes left. Any questions on anything so far? Yes? Yes. So the link protection is not supported in iOS. Does the same apply to iOS XE? Yes. Yes, yes. From a control plane of point of view, and that's where everything starts, iOS and iOS XE is the same, right? But no, never, no plans. I'm betting it will not happen. So in the beginning, we actually it's a good question because some history. In the beginning, we started with per-link, probably because it was easier to code and get it out there quicker, and some people deployed it. But then we had per-prefix, and everybody's using that, and also the people who had per-link kind of migrated. So I haven't seen per-link in a long time, and I don't see a burning reason why to configure it or to use it. Key takeaways. We have seen some theory and then the configuration, troubleshooting, and so on. First, on direct LFA. For some people, this is good enough. It works. You can use it for IPv4, IPv6. You don't need MPLS. You're good. For some people, the topology is not so good. It's not meshed enough. So you might need remote LFA. But you need MPLS. You need LDP, targeted LDP. But you get a lot more coverage. Well, if your topology is really bad, let's say, or you already have segment routing, just do TI-LFA. It's really beautiful. You get 100% coverage. It's easy to track, easy to configure. It's easier than remote LFA. So really beautiful thing. This is, to me, one of the big advantages also of segment routing. Not the only one, but a big one. Right? And finally, yeah, LFA. It's easy to deploy. It's incremental. You can start on one router and then deploy it. Signaling protocol, one command to configure. Easy to troubleshoot. I wouldn't say difficult. So a lot of reasons why you should try it out. And it comes for free. There's no license to pay for LFA. We have it on almost all our platforms, iOS and iOS XR. Yeah, Cisco Spark, it's still live for the next 2 weeks, I believe. If you have a question, just ask. The PDF is on the app. It's on Spark. I gave you the link. There are no other sessions to do anymore. We are done for the week. This was Cisco Live. This was this session. So thank you for staying until the end. Thank you for being at Cisco Live. If you have any other question, please ask me now or on the Spark room. Thank you.